So we're back online with our next presentation. It'll be the third in our live stream short course. We're again back here with Dr. R. Kerry Rowe from Queen's University in Kingston. And this next presentation from Dr. Rowe will be on the effect of wrinkles on geomembrane performance, which has been a topic of great concern and conversation today and recently in the last 6 months to a year within the industry. So let's welcome again Dr. Rowe.
Well, thank you very much. It's good to be back up here to talk about wrinkles and their effect on geomembrane performance. So let's begin with the basics. Why we use a geomembrane, everybody probably knows, is because they are essentially impermeable to aqueous solutions, except where they have holes. Now, Giroux's been saying for almost 30 years, most recently in his 2017 paper, all liners leak. And the advantage we have today that we haven't had all that long is that with electrical leak location surveys, we have some idea of what the number of holes would be if you have proper quality assurance but no electrical leak survey before you cover it. And based on that data, it's of the order of 5 to 6 holes per hectare. But that's with really quality, full-time construction quality assurance like Glenn was just talking about. If you have people just documenting and occasionally looking, then you're more likely to be at 25 holes per hectare. So if we're going to talk about leakage, it's going to depend on the number and size of holes. And that's the number and size of holes when you are in service. So even if you do have a leak location survey, that will get rid of the ones you pick up then, but additional holes can appear as you load it up if you do not have the right design conditions. Leakage will depend on the head on the liner, and very importantly, as we'll be discussing, the interaction between climatic conditions and the surrounding media, both above and below the geomembrane, both before and after it is covered. Now, the traditional way of calculating the leakage through a geomembrane has typically been assuming that your geomembrane is in direct and intimate contact with a clay liner when you're dealing with a composite liner. And the equations often used are based on Giroux 1997 or some variation thereof, which is an empirical effect to an analytic equation. And it is considering the situation you see here. There are no thermal wrinkles in this photograph. We will come back to that. But first, let us just remind ourselves of the effect. See if I can get rid of this. The effect of assuming we have direct contact. And we want to model the leakage. And this is what is essentially in the Giroux equations. We have a hole of radius r0, and fairly obviously directly beneath the hole, the leakage through the clay liner is given by Darcy's law. However, that is only a small component of the leakage because there is also going to be leakage at the interface between the geomembrane and clay liner. There is a transmissivity to that interface, which is a second very important hydraulic parameter. So yes, the hydraulic conductivity of the clay liner is important, but so too is the transmissivity because they control the wetted radius. This is the area over which leakage is going to occur. So in 1997, Giroux defined good contact as a geomembrane with as few wrinkles as possible on low permeability soil, adequately compacted and a smooth surface. and poor contact as a geomembrane with a certain number of wrinkles and or on low permeability soil, not well compacted and does not appear smooth. Now this is all right as long as you interpret wrinkles in this context as being minor little undulations no more than about a centimetre maximum high. You cannot model the wrinkles I'm going to be talking about by interface transmissivity. You have to model them explicitly. Now, if you look at the Rowe equations, they are based on an analytical solution that included hydraulic conductivity and transmissivity. And Rowe fit an empirical equation to it, but built into that are assumptions about transmissivity. And good contact corresponds to a transmissivity of about 2 times 10 to the minus 8 meters squared per second. Poor contact corresponds to a transmissivity of about 10 to the minus 7 meters squared per second. So whether you realize it or not, if you're using those equations, you are assuming a transmissivity. So what do we know then? We know that if you have good contact, you are going to have good performance, but you're going to get better performance with a GCL than a compacted clay. And the reason for that is that it's easier to place a compacted clay, easier to place a GCL where you have a good foundation that is nice and flat and smooth. It's more difficult to achieve that with compacted clay. Furthermore, bentonite swells when it hydrates. And that swelling of the bentonite tends to fill minor little irregularities, tiny wrinkles, not the wrinkles I'm going to be talking about. But because of those two reasons, the transmissivity of the interface between a geomembrane and GCL at stresses of about 50 kPa and higher is between 2 and 4 times 10 to the minus 11 meters squared per second. Those numbers may not mean much to you, but if you compare them to the ones for compacted clay, they're 3 to 4 orders of magnitude lower. And that is why we get lower leakage generally with a GCL than with compacted clay. Now we're going to be focusing mostly here on the issue of geomembranes in composite liners. But we need to begin because we are going to be talking about wrinkles, and where you have a wrinkle, you basically have a geomembrane with air below it if there's a hole in the wrinkle. So what is the leakage you could get through the hole if there's no clay liner? Or the same question if that geomembrane is sitting on a drain. Then if we had a hole of diameter 1.4 millimeters and a head of 0.3 meters, the leakage would be 750 litres per hectare per day. If the hole was 1.8 millimeters in diameter, it's 1,250. 2.3 millimeters, it's 2,000. If you have two of them, it's 4,000. And if it's 3.2 millimeters, it's 4,000. Now, I didn't pick these numbers at random. I looked at the typical holes that are found in leak location surveys and reported by Rowe, and that's what I based this on. And if you take that, you get a leakage of 10,000 litres per hectare per day. But the point is, any one hole, even though they're small, allow a lot of leakage. Okay, so now why do we use composite liners? If we have the same 5 holes, but a composite liner with a GCL, and we're going to assume a hydraulic conductivity, and in fact, I'm going to assume the transmissivity for good contact that Rowe got, which is several orders of magnitude higher than what you can expect, and still our leakage is only 0.2 litres per hectare per day. And if we have a compacted clay with typical good parameters, we have 2 litres per hectare per day. The GCL is at least 10 times better, but they're both remarkably good. they are both negligible leakage. So if you look at field monitoring, what do we find? We find the leakage with composite liners is much less than with a single geomembrane, just as those calculations suggest. We find that composite liners with a GCL perform much better than composite liners with compacted clay, just as those calculations suggest. But we also discover that the observed leakages are 10 to 10,000 times larger than calculated from those traditional equations. So why is that so? Here is a schematic. In the upper left-hand corner, you see a detail from a typical engineered drawing, showing a geomembrane as a nice straight line sitting in direct and intimate contact with the underlying clay liner, in this case a GCL. And indeed you can get that in the field. You see it here at our Quelt site, Queen's University liner test site just north of Kingston, Ontario, on a cloudy November morning when the ambient temperature is 3 degrees C. There are no thermal wrinkles. And this is what's assumed in the Rowe equations or its implementation in things like the HELP model. This is exactly the same site on exactly the same day a little later. The ambient temperature is only 17 degrees, but the geomembrane in the sun is 45 degrees Celsius. And because of thermal expansion, wrinkles develop. You'll notice that there are a set of wrinkles running parallel to the roll. They have a V shape, and they're very consistent. Why? Because of how the geomembrane was manufactured. It was a geomembrane from a blown film with a round die. It comes out of that round die as a bubble. It's pulled up the cooling tower and then passes between some nip rollers, which squash the film like this. And obviously, we get folds. Then we cut it, unfold it, and put it on a roll. And if you look at the roll, unless you really know what you're looking for, you won't see it. But there is a little dimple at the quarter points. However, when you put it in the field and it gets hot, you have no trouble seeing it. There will be wrinkles running parallel to the roll at the quarter points. And here you see one. There you see a seam. And what do we also see crossing that seam? We see wrinkles. So if we have a defect in the seam that's not picked up by the QA people, and that seam is connected to a wrinkle, suddenly it becomes far more significant. Indeed, if you get a hole anywhere in a wrinkle network, fluid can migrate to any other location with virtually no resistance. So beneath the wrinkle, you are relying on the clay liner to control your leakage. And in this photograph, you can see what the network looks like. It turns out that it is no more complicated to calculate the leakage with a wrinkle than it is without one. It's a one-line equation. You can do it on your cell phone these days. Let's look at the mechanics here. If we have a wrinkle of width 2b and a length L, then the leakage directly below the wrinkle is going to be given by Darcy's law, traditional geotechnical engineering. So it's going to be the area, which is the width times the length of the wrinkle, the hydraulic conductivity of the liner below the wrinkle, Kb, and the hydraulic gradient across the wrinkle. But that is one of the components. There is also going to be a lateral component away from the wrinkle in the interface. This is the same interface transmissivity we talk about when we have direct contact. It's the same issue. And we can get an equation for that horizontal leakage. It's equal to the length of the wrinkle times the transmissivity of the interface times the horizontal gradient. And we can get a closed form solution for the horizontal gradient. And we end up with this equation. So the leakage, where you have a wrinkle of length L and width 2b, is going to be related to the hydraulic conductivity Kb beneath the wrinkle, and to the hydraulic conductivity Ka, where the geomembrane is in direct contact with the GCL. And these will generally not be the same, because below the wrinkle you have zero effective stress. And effective stress has a significant effect on the hydraulic conductivity of GCLs. So you'll have a much higher hydraulic conductivity below the wrinkle than you will where you have a good stress because you have direct contact. So you need to consider two hydraulic conductivities. And of course, we have the hydraulic gradient. So it's a simple matter to do the calculation. It's the same transmissivity we would use in direct contact. The new things here is that we have to remember there are two hydraulic conductivities we have to deal with, and we need to know what the length and width of the wrinkles are. So let us talk about that. It is more than 20 years ago since I published that equation. But the question then became, what is the length and width of the wrinkles? So to go out and answer that question, we used high-resolution photography, initially with a helium balloon, these days with a drone, and we photographed sites, various locations, various times of day, various times of year to try and get an idea how wrinkles behave. Here's one such photograph highlighting a few features. You'll see there are geomembrane seams. You'll notice that there are wrinkles running across those seams. So we have wrinkles running perpendicular to the roll. We have our peaked wrinkles running parallel to the roll. And we have some random wrinkles just to make life more interesting. Those ones that cross the seams are particularly important because of not only the possibility of holes in the seams if you don't have good quality assurance, but they are also where the greatest weakness in your liner is located, at the seam. When we document this, we're interested in a number of quantities. We're interested in the length of individual wrinkles. We're interested in their width. We're interested in the area beneath the wrinkles. And we're very interested in those wrinkles that are hydraulically connected. Now, in this conversation, if you look at this photograph, we've highlighted the wrinkles we're looking at in red. They're not the only wrinkles. We didn't calculate anything for a wrinkle less than 3 centimeters in height. So we have a threshold at which we call it a significant wrinkle, and it's about 3 centimeters. There you see the wedge-welded seams. And here is an aerial photograph, and you can see the network of wrinkles that is there. And if we join up all the hydraulically significant connected wrinkles, that is your interconnected network. So let's look at data over a day period. We're going to go just north of Toronto to a cell about 60 meters wide, 140 meters long. You get an idea of dimension from the roll width shown in the photograph. And you can see one of the photographs showing you the wrinkles. We are going to look at that where we highlight in red what we are counting as a significant wrinkle. This is one we believe will still exist after the geomembrane is loaded. And I'll come back to that issue shortly. But you can see early in the morning, we have essentially lines horizontal or parallel to the roll. They are all what I talked about as peaked wrinkles. And at that time, there's not a lot of connectedness of individual wrinkles. Here it is around midday, a very different story. And you can see a very interconnected network of wrinkles. So let us take data like that and plot it as the length of wrinkle, this is the longest connected wrinkle, versus time of day. This is in June, on a sunny day in Canada. And you can see that if we were to cover it before 9 in the morning or after 5 p.m. in the afternoon, our longest wrinkle would be about 200 meters. Now, I want you to remember that number because I'm going to come back to it in a calculation shortly. You can see that if we covered it before 10 in the morning or after 4 in the afternoon on that day, our longest wrinkle would be 1,000 meters, which I'll also talk about. Now, if you're really careless and covered it between 11:30 in the morning and 2:30 in the afternoon, your longest wrinkle is over 2,000 meters, or if you like, feet, over 6,600 feet. Now, what is critical is not the wrinkles there at any time of day, but the wrinkles there at the time of day you cover the geomembrane. Because when you cover them, they will get a little smaller, but if they're more than 3 centimeters to start with, they will not go away. Now, I talked about length. I want to talk a little bit about area of wrinkles. So here I'm plotting data from a number of different sites at a number of different times of year. And indeed, the results vary with time of year because they're related to solar radiation. If we plot the percent of wrinkles versus time of day, and we wanted to keep below 5%, and I'm going to use 5% in an example, but 5% generally at all of these sites we would have to cover before 6:30 in the morning or after 5 p.m. in the afternoon. Now in winter we have a longer window, but generally we would prefer not to construct in winter. If we wanted to keep the percentage to 15 to 20%, we would have to cover before 7:30 in the morning and after 5 p.m. in the afternoon. Not much of a gain. Now you can see why Glenn's out there at night time checking geomembranes. So why does it matter? Well, let's suppose we have 5 holes per hectare and 20% of our site is occupied by wrinkles. Then you can show very quickly that there is a 2/3 probability that at least one of those holes is going to be in a wrinkle. If we only have 5% height, that probability drops to 23%. But either way, there is a reasonable probability that wrinkles will dominate the leakage unless you cover with virtually no wrinkles. So one hole in a wrinkle is going to have a dramatically greater effect than 5 holes without a wrinkle. There is a relationship between the length of connected wrinkles and the area below wrinkles. And here you see data from a number of different landfills, in some cases with a GCL, some cases with compacted clay, some cases with sand below the geomembrane. And you can see that if we kept the area below wrinkles below 5%, our longest wrinkle would be less than 200 meters. If we let it get to 15%, depending on the site, the time of year, it could be 400 to 2,000 meters. At 20%, we're 400 to 2,600 meters. And of course, if you let it get to 30%, you've got some very long wrinkles. So to summarize, wrinkling's related to solar radiation and geomembrane temperature. And a black geomembrane can easily be 20 to 40 degrees hotter than ambient. In our studies, a typical wrinkle as we define it is 0.2 to 0.3 meters wide. It's about 6 centimeters high on average, but can be as much as 20 centimeters. And wrinkles can range from a few percent to more than 30% of your site at any one time. Even a small area, less than 0.2 of a hectare or half an acre, if you've got 5% of the area, your wrinkle is getting to 200 meters. So if you want to get below 200 meters, less than 5% of your area is wrinkles. Now let's address the question of burial. And some very nice work done by Sung and by Brackman and his students has shown that what we are defining as a significant wrinkle does not go away. Yes, it gets smaller, but it does not go away. There's quite a lot of literature on this. I'm just going to show you one example where Godina and Brackman placed a sand foundation, they put a geomembrane with a wrinkle, and they had a sand subgrade above it. This wrinkle I'm going to show you is 200 millimeters wide initially and 60 millimeters high. Under about 18 meters of waste, or 250 kPa, it reduces to about 80 millimeters wide and about 30 millimeters high. But it's smaller. It didn't go away. Even under 80 meters of waste, or 1100 kPa, it's still 60 millimeters wide and 30 millimeters high. And you can see from the shape there are strains in that geomembrane. And this is about as best as you can do with sand. If you have gravel, you will get larger wrinkles, not smaller, because of better arching. So to summarize then, as many as 5,000 wrinkles per hectare we've observed. The maximum length of wrinkle is up to and beyond 5,400 meters. And if you want to keep the number of wrinkles down that are going to affect your leakage, you need to limit the time of day you want to place the cover. As Glenn was saying, cutting out wrinkles and placing inferior wells is not a good solution. So wrinkles may get smaller, but they don't go away after you cover them, and they don't go away under the weight of the waste on top of them. Now that data was for HDPE. If we have LLDPE, it will also wrinkle. The coefficient of thermal expansion is not that different to HDPE, but its stiffness is a little different, and that will affect the location and size of wrinkles. But you also have to remember that if you're going to compare wrinkles, thickness will also have an effect. So it is the stiffness of the geomembrane that's critical. Be careful comparing LLD and HDPE unless you're looking at the same thickness. Here's another photograph of an LLDPE liner with wrinkles. So using LLDPE doesn't mean the issue has gone away. What can we do to reduce wrinkles, or, put another way, to increase the number of hours of day that we can cover the geomembrane? One possibility is a white geomembrane. So let's explore that at exactly the same site, under exactly the same thermal conditions on the same day. So here we are at Quelz, and we are in early spring. The snow is only recently gone. We're at the 18th of May. And you can see at night we're down to 2 degrees Celsius. In the day we get up to 20 degrees when it's sunny. Here's the black geomembrane. When ambient's 20, it's up at over 50 degrees Celsius. You'll notice that even at night it's hotter. The reason for that is when it gets hot during the day, some of the heat gets stored by the subgrade at night and keeps it warmer. And here's the white geomembrane right beside it. And you can see it is 20 degrees cooler. And that, you might expect, is going to have an effect on the wrinkles. What if we put on a white protection layer? So here we have a black geomembrane, and then just before noon we place a thick 1,000 gram per square meter white protection geotextile on the geomembrane. So it comes straight off the roll. On the roll it's relatively cool. It's got a fair mass at 1,000 grams per square meter, and you can see it quenches the temperature very quickly. And we then follow the white geomembrane curve until the evening comes, when the heat that was stored while it was black keeps it warmer. So what's that do to wrinkles? Let's take a look. At 8 o'clock in the morning, our black geomembrane is already at 26 degrees Celsius. Our white is at 15. So we already have 11 degree differential at 8 a.m. We have highlighted here the longest connected wrinkle, hydraulically connected wrinkle, in green. And you can visually already see we have longer wrinkles for black than we have for white, even at 8 in the morning. If we go to around midday on this particular day in the early spring, our black is at almost 50 degrees Celsius, our white is 20 degrees cooler at 30 degrees. Again, the longest connected wrinkle is in green, and you see a significant difference. Where you really see the difference is at 5 in the afternoon. Our black geomembrane is still at 45 degrees, our white is at 27, and look at the difference if you add up the length of the green sectors in the two pictures. So white does make a difference. We can get significant wrinkles in both black and white. However, they appear sooner and remain longer when you have a black geomembrane than a white geomembrane. You'll get more wrinkles at any time of day in black than white, and as a consequence of that, you'll get longer connected wrinkles in black than in white. So let's come back to number of holes and probability. So if we have 5 holes per hectare, as we saw before, and we have 5% covered, we have a 23% probability of a hole in a wrinkle. At 15%, we're at 56% probability. At 20% wrinkles, we're at 67%. Now, the typical range is 5 to 6 holes per hectare with good quality assurance. Let's assume Glenn's there looking after it for us. At 15%, we go from 56 to 62% probability. Here we have 10 holes per hectare. And now we're going from 5% coverage at 40% probability to, at 20% coverage, essentially 90% probability. So you can see that if you don't keep those wrinkles tightly controlled and keep the number of holes down, chances are that your leakage is going to be controlled by a hole in one or more wrinkles. That this is true is evident from a very nice paper by Beck in 2015, plotting data from well over 100 cells where there are double-lined landfills in New York. And if we remember the 5 to 6 holes from Rowe, which is also based on leak location survey data, we can see that if you remember the numbers I showed you for direct contact, 0.2 litres per hectare per day for a GCL, 2 litres per hectare per day with a GCL, with a CCL, and here they're essentially all at 10 or more litres per hectare per day. This is suggesting perhaps that there are wrinkles playing a role, or there are a humongous number of holes, which is not likely in that application. You can see it ranges from, I think the first marker there is at about 15 litres per hectare per day to well over 1,000 litres per hectare per day. And this is another very interesting plot from that same paper by Beck, and it shows the probability of the leakage rate exceeding a certain value if you do not have a leak location survey and fix those holes. And you can see that at 50 litres per hectare per day, which is roughly about 5 gallons per acre per day, there's a 60% probability you're going to seed it. At 200 litres per hectare per day, or about 20 gallons per acre per day, there is a 20% probability. And this is telling us very clearly that wrinkles matter. So let's look at some numbers. If we have compacted clay, and we're assuming a good clay liner at 10 to the minus 9 meters per second, good interface conditions as defined by Rowe, a 1,000 meter long wrinkle, a 0.3 meter head, and 1 hole in 1 wrinkle, the leakage is 830 litres per hectare per day. The probability of exceeding that based on the New York data with good quality assurance is less than 3%. Of course, if you didn't have good quality assurance, it gets higher. If we have a wrinkle of length 230 metres, our leakage is 190 litres per hectare per day, which is approximately 20 gallons per acre per day. And in New York State, that primary liner has got about 20% probability of exceeding it. And if we go to 60 litres per hectare per day, that's 60 metres per hectare in wrinkle length. That's 50 litres per hectare per day, or about 5 gallons per acre per day, is what we would get. And there's about a 60% chance of exceeding that without a leak location survey. If we go to a GCL, you can see it is demonstrably better in the calculations as it is in the field. For a 1,000-metre long wrinkle, we go from 830 to 130 litres per hectare per day. At 400 metres, we're at 50 litres per hectare per day. So you can see we can get 50 with a 60-metre long wrinkle and compacted clay, 400-metre long wrinkle and a GCL. So the wrinkle has less significant effect with a GCL. And if we go to the 60-metre long wrinkle, then we are down to 8 litres per hectare per day. That is a very low leakage. For a landfill, at that leakage, diffusion will be a bigger concern than advection. Now, I hope I've made the point that controlling wrinkles is important at the time of covering them because of the effect they can have on leakage. Wrinkles can have another couple of effects if you leave your liner exposed for a long period of time, which can make things worse than I just showed you a moment ago. Let me explain why. When a geomembrane gets hot, and even in Canada it can get to 60 to 70 degrees Celsius, hotter in Texas. The GCL, or if we have compacted clay, they both have water in them. GCL sucks it up from the foundation even you place it relatively dry. When the geomembrane gets hot, that water evaporates and it goes into the airspace. And where is most of that airspace? It's at the wrinkles. So the water is migrating towards the wrinkles. And when the geomembrane cools down, it condenses, with most of it condensing below the wrinkles. It doesn't go back to where it came from. Now, that can have a number of consequences I'm going to explain to you. But first, let us remind ourselves that if we have a composite liner with a GCL, then we are laying down GCLs, which are also a manufactured product, they come in rolls, in panels. And we overlap those panels. And the most commonly used GCLs have a geotextile above and below the bentonite. And if we put two geotextiles together, we have a very permeable interface between them, unless we do something to stop it. So what do we do to stop it? We place supplemental bentonite. Now, depending on the manufacturer, there are 3 basic different ways of achieving this. One manufacturer burns a groove in one of the geotextiles so that the bentonite falls out to cause a supplemental bentonite to interrupt flow that would otherwise occur between the geotextiles. Another manufacturer places about 400 grams per metre of powdered bentonite between the 2 GCLs. And a third manufacturer impregnates the bentonite. And if done properly and if you cover it in a timely manner, all 3 methods will work. But if you allow your GCL to go through cycles of wetting and drying, it can shrink. Now, let's suppose it shrinks but doesn't form a gap. That doesn't mean we have no problem, because as soon as it shrinks away from that supplemental bentonite, we now have geotextile on top of geotextile. Geotextiles are very permeable. We have a very clear path for water to flow between the overlap. And if it's that seal, let's say a burn in the Geotextile, it's located about 7 to 8 centimetres from the edge. Once you've had about 7 centimetres of shrinkage, you no longer have a proper seal. Of course, it's even worse if a gap forms. And remember, if you have a geomembrane on top of this, you can't see what I'm showing you. You don't know this has happened unless you open up the geomembrane. So we originally built quilts for 2 reasons. One was to look at wrinkles, I've talked about that. The other was to look at shrinkage. We used the 4 most commonly used GCLs in North America, side by side, so we had an apples to apples comparison. And we monitored them for almost 5 years. And here we're plotting the reduction in overlap versus time for 2 of those products. You'll notice that GCL2 had virtually no shrinkage in almost 5 years. It is manufactured in a different way to GCL4. GCL4, I'm showing data for different panels, and if we were to follow the manufacturer's recommendation and put 150 millimeter overlap, then by the time it had shrunk 75 millimeters, it was disengaged and not functional as a proper seal. And here you can see that would have occurred in less than 2.5 years. We in fact placed it with a 300 millimeter overlap, so that panel, even though it shrank about 150 millimeters, would still be okay. Not so for another panel of the material, which had shrunk more than 300 millimeters in less than 2.5 years and had shrunk over 400 millimeters when we terminated the experiment. And here you can see a photograph of it, over 400 millimeters of shrinkage and a gap. Well, you might say, that's not good. Clearly, if you've got a hole directly over it, that's going to give you a lot of leakage. Remember how much leakage occurs when you don't have a clay liner beneath your geomembrane? A lot. But what are the chances of a hole in the geomembrane aligning with this? Well, the answer, as we will see, is very high. So here's an aerial photograph showing a wrinkle network with 4 different products. It actually varies a little bit depending on the product. I'm going to focus right here on GCL4. And looking in detail at that, we see we have a set of orthogonal wrinkles. We have one set 3.3 meters apart. They are the peaked wrinkles we talked about, the V-shaped wrinkles at the quarter points. You can see the seams above and below, and that is one set of wrinkles. You'll see there's another orthogonal set at 4.4 meters. Why do they keep repeating themselves at a 4.4 meter spacing? Well, we remember that wrinkling tends to occur where there's some irregularity in the foundation. And where you have an overlap of GCLs, you have an irregularity. And so a location preferred for a wrinkle. And where are those overlaps we've just been looking at? Right beneath those wrinkles. So, what's the probability of a hole taking water to that gap? Well, if that hole is anywhere in that interconnected wrinkle network, it can get to that gap. It doesn't have to be right on top of it. Now, if we go a little bit south of that, it's a little better. You can see there has been some movement, but we don't have a gap. Does that mean we don't have a problem? Well, let's examine that. We are going to do a 1 meter diameter rigid permeability test in a very large GLS. We are measuring the leakage, and as a baseline, we're just putting a GCL in, single panel. Essentially, this is a hydraulic conductivity test, and that's what you see for the single panel. Here we put a proper 150 millimeter overlap, and the leakage gets a little less. There's a bit of preferential flow at the interface, even with supplemental bentonite, but that's more than counted by 2 layers of GCL. And so we get a slight reduction in leakage. Now let's let that overlap get reduced to 50 millimeters. So the supplemental bentonite is not engaged. And the leakage went up 1 million-fold. 1 million times increase in the leakage. Yet, if you looked at it from above, it would not be obvious. So, shrinkage depends on the method of GCL manufacture. They don't all shrink the same. But it also depends very much on local site conditions. If you want to minimize the effect, the best solution is in fact to do what all of the reputable manufacturers recommend: cover it in a timely manner. If you do that, shrinkage is not going to be a problem for you, nor the next little problem I'm going to talk about. So it's always a good idea to follow the manufacturer's instructions. If it's impossible to do so, think about it at the design stage, because some GCLs are much less prone than others. Select one with good performance. Put in a 300 millimeter overlap. Where you can, heat tack it. That is not a solution to the problem, but it certainly can help if done properly. A white geomembrane reduces the thermal cycles, and that helps. But the best thing to do is to cover it in a timely manner. Now, those are the things we were looking for when we built quelts. However, we got another little surprise. We were studying it without opening up the geomembrane for 3.6 years because we didn't want to disturb our wrinkles. But after we finished that, we opened it up. We looked at overlaps. But what in particular we found was what we call downslope erosion. Now, I'm going to get to that, but I want to point out to you that wrinkles don't just occur in summer. Here you can see our site in winter, mostly snow-covered, and where that snow is off it, you can see significant wrinkles because it's in the sun and it heats up, even in winter. This is to convince you that the wrinkles we're talking about are not due to poor construction. If you look at the left, there are a few construction wrinkles at the well, but they're very, very small. These are the sort of wrinkles you might talk about in the Giroux context. But if you look at the right, you see significant downslope wrinkles, you see lots of cross-roll wrinkles, and they all contribute not only to shrinkage, but even more importantly to what I can call downslope erosion. So both shrinkage and downslope erosion occur because the water is taken up from the GCL, from the subsoil, as it's supposed to do. When it heats, water is lost to the interface between the geomembrane and GCL. It migrates to the wrinkles. When it's cooled, that water condenses on the underside of the geomembrane, and then it starts to run downhill. And it gets to something that causes the water on the underside of the geomembrane to drip, drip, drip on the GCL. And just as a dripping tap can drive us crazy, dripping will drive our poor GCL crazy. So this was the first clue we had of what was going on. You see these little rivulets. At the bottom of the slope, if you were there at 6 o'clock, you could feel at certain low locations you were on a waterbed. If you opened it up, you certainly were. An hour later, it had evaporated again. You wouldn't even know it was there. Then, a little later, we started to see staining. And what do we find at the bottom of the slope? Significant bentonite. And where is this happening? Well, one key location, look down this peaked wrinkle. Now we're going to fold back the wrinkle and see what's beneath it. See this white area? The bentonite has all been eroded. In fact, of the 4 products he tested, only one of them really showed it clearly to the naked eye like this. The other ones we had to work really hard to find. And you'll see there's downslope wrinkles, but there's also wrinkles that are giving erosion across the width of the roll. We've highlighted in orange paint, so you can see it in an aerial photograph, some of the key wrinkles. You can see one here running from top to bottom of the slope. This is after we just fold back the geomembrane early in the morning. You can see the water on the geomembrane. You can also see where bentonite is accumulating around a wrinkle. This is when it dries. Now that water runs down until it hits something. It could be a wrinkle, it could be a weld, it could be simply a little irregularity in the foundation. And once the bentonite starts to erode, it goes somewhere and it accumulates. The last example was one big accumulation in a small location. Here's an accumulation but more spread out. Here you can see where there has been erosion. And when we lift up and take that specimen out, you can see bentonite on the foundation. Here's a particular feature that we found after 3.6 years. We cut it out to take back to the lab. It's 1.5 meters long, 0.6 meters wide. And in the lab, we x-rayed it. The coin is giving us this white as a scale. And where you see the dark region is where all the bentonite has been eroded. Where you see a dappled region, that is desiccated bentonite. Now we took little specimens across 5 different cross sections and actually measured the mass per unit area of bentonite. I'm going to show you in detail 2 of those. And here we're playing dry mass versus position. And the average bentonite mass per unit area is shown in yellow. And you can see there's an almost 200 millimeter wide eroded area in section AA and more than 200 millimeter wide in section DD. This is where we took that patch from. We replaced it with a GCL. We came back and looked at it a year later, and it too was eroded. That erosion was occurring in very consistent locations and very repeatably. So here you see a section where we've highlighted the eroded areas in orange paint. And of course there are the long one I pointed out, but there are lots of shorter ones that are also potentially problematic. And it didn't just occur on the boats. This is a different GCL, as you can see, and you can see one running from one end to the other of this panel of GCL. And here it's been cut open and you can clearly see there's no bentonite. That's what it looks like when we highlight it in an aerial photograph. This is another feature, 30 centimeters wide, 1.4 meters long. That's what it looks like looking at it from above in normal daylight. We have a special light panel we can slide beneath it to inspect, and this is the light shining through. Where you see white, that's light shining through the geotextile. Where you see the dark areas is where you've got the bentonite. We actually have a portable dark room. It's called a big cardboard box where we can take photographs in the dark. And this is the light shining through. You can see it much more clearly. Where there's no bentonite, it's white. Where we've got a hydrated bentonite, it's black. Where it's desiccated, it is dappled. So white geomembrane prolonged the time to erosion, but didn't stop it. However, some GCLs were far more resistant than others. It depends on the bentonite. It also depends on how the GCL is manufactured. We used a multi-component GCL with the plastic facing up against the geomembrane, and that eliminated the problem because it cuts off the mechanism. But we also tried just doing what the manufacturer recommended and putting cover soil on in a timely fashion, and that solves the problem. If we have a hole in a geomembrane and it aligns with a seam that shrinks, only has to shrink enough to disengage the supplemental bentonite, and clearly if it forms a gap, or if we have downslope erosion, then our leakage is now controlled by Bernoulli's equation. And that can be quite large, even for a 1.4 millimeter diameter hole. The probability of this happening becomes much higher as the number of buried wrinkles increases, since the wrinkles can be both perpendicular to and parallel and over the overlaps. They are also, not by accident, aligned with the location of downslope erosion. So, assuming you wish to avoid this, as I would hope, cover the composite liner in a timely manner. This is important for most common GCLs. I haven't talked about it, but it's equally important for compacted clay because it will desiccate, and that significantly increases the interface transmissivity that controls leakage. If you must leave it exposed, then select a GCL with proven resistance to shrinkage and downslope erosion. And they do exist, but they are quality products that will cost you more. Minimize the number of buried wrinkles, less than 5%. And clearly the other thing you can do is minimize the number of holes with an electrical leak location survey. And I'm sure Sam will be telling you all about that. So the nature of liner required depends on the level of acceptable leakage. You can substantially reduce that leakage with a composite liner and especially with a GCL. Wrinkles and waves will increase leakage for composite liners and should be minimized. As the area percentage covered by wrinkles increases, so too does the probability a hole will intersect a wrinkle, that the wrinkle will be long, and that your leakage will exceed your action leakage rate. Composite liner leakage is less with a GCL and compacted clay, but your advantages get smaller the more the area of wrinkles because you have low hydraulic conductivity where you have no wrinkles, you have higher hydraulic conductivity where you have wrinkles. They affect the temperature distribution. A white geomembrane will help. It gives you longer when you can cover, but it doesn't eliminate the problem. Cover soil and loading reduce the wrinkle width, but they remain. So cover them in a timely manner to minimize desiccation, shrinkage, and downslope erosion. And they all become even more critical if you have significant buried wrinkles. Thank you.
Thank you, Dr. Rowe. That was excellent. Very, very informative. We are up against our lunch break, but we have a couple questions, or at least one question from our webinar audience. Actually, just a statement. I think you kind of addressed it a little bit here, but the question from Martin Brungard was, it appears lined impoundments with a GCL underlayer are subject to this shrinkage since they are exposed for years. So can you comment a little bit more about the types of applications that you're going to see potential for more shrinkage with the GCL?
Well, certainly the case that was just covered. Unfortunately, often people want to build the entire liner long before it's going to be covered. And so particularly on side slopes, liners can be left exposed for years. That's
Right.
what in fact prompted us to start this study, was the question, what's the implication of that? It can definitely be a problem, as I've tried to illustrate, but if you can't cover it, then what you need to do is put a bit more attention into your design, select the products that minimize your risk, and minimize your number of holes. Those are the two things you can do.
Okay. Here's a really...
Can I just...
Go ahead.
That means good design, good quality assurance.
Gotcha. Here's a really good question from Talia De Silva. Have any tests been conducted comparing peak wrinkle length between blown film and flat die extrusion films or geomembranes? Would that connected wrinkle length be improved by specifying the use of flat die materials, removing those dominant peak waves?
Unfortunately, we don't have the data to give you a clearly quantified answer, but I can give you an observational answer. Firstly, the coefficient of thermal expansion is essentially the same. They both got to expand. Really, the only difference is that whereas with the blown film, you know you're going to get some at a very, very regular location. You're still going to get the same total amount of wrinkling. Its location's just not going to be quite as predictable.
Right.
In my observation in the field, you can get quite a lot of it migrating to wells. But it's going to be there. It's going to be wherever there's irregularities that encourage it, because wrinkling is a buckling phenomenon. And buckling will occur wherever there is something that gives it a slight preference to change out of plane.
So would you recommend using white geomembranes in every application, or just where the temperature is hotter than others, like in India?
Well,
Or
I
That
don't
was a
think
question
India
from,
is the only place where
question
you
from
get
the- yeah.
high temperatures. I would
Yeah.
even say, where I live in Canada,
Yeah.
from a construction perspective, you get high temperatures. So I would use white wherever you're concerned about this issue and
Sure.
you want to open up your opportunities. That doesn't mean I would say use white everywhere. I would depend on the circumstances.
All right, we got a couple questions from the live audience. Sam.
Kerry, thank you for the presentation. Wonderful. In the context of material design, to respond to wrinkles, to respond to intimate contact, to respond to long-term beneficial hydraulic performance, is it time to consider really an emphasis on a low bending stiffness material?
Do you want to repeat the question?
So Sam says, because of this pervasiveness, I guess, in seeing this, is it time to start really paying attention to a low stiffness material, or a low,
To answer your question, yes and no. Conceptually, yes. I mean, there could be significant advantages, at least from what I was talking about in this particular talk, in reducing the significance of wrinkles. But we also have to be very careful. HDPE is being used extensively. We've got 30 years of good experience plus an awful lot of research that goes into it. I would be very wary of changing because of one issue without putting the research in that really shows that you've addressed all the other issues that can come up. Unfortunately, I've seen too many years in my life where people have come up to a quick fix to a problem and created another bigger problem. So if the research was done and proved that it didn't create other problems for us, I would say yes, but beware of unintended consequences.
Great question. Dr. Stark?
Kerry, thanks again for visiting the University of Illinois. If I have time for two questions.
Sure.
First is, at the Queens external facility, you had a photograph early in the morning and later in the day. My question is, are the wrinkles elastic? In other words, when you got later in the day and it cooled, did it fully remove the wrinkle? And then if it doesn't, so that means it's a progressive growth of wrinkle.
Let me restate that. So Dr. Stark asked a question in one of the pictures that Kerry showed earlier, the Quelch facility. There were some early morning pictures and late afternoon pictures with more wrinkles than others. As those wrinkles subside, are they elastic? Do you see them start to really return back to original shape with that temperature delta?
Very good question, and indeed that was one of the issues we were looking at. We, and more specifically the graduate student, Melissa Chappell, doing that work, was out there at various times of the day or various times of the year, and that's why we had our own site. At other sites you got in and got a snapshot, but invariably they wanted to cover it up and use it. At our own site we could leave it and go back and take photographs from exactly the same position, and what we found was it was very elastic. Those wrinkles would go away on a cool night and they come back to, certainly the significant ones, to exactly the same spot the next day. And that's why we kept getting this downslope erosion. If they kept moving around, the water would be distributed more uniformly, but because they kept coming back to the same place, it was concentrating the issue and causing the problem. So in our case, at least, where we studied it for over 3 years, the wrinkling side of the study, we found they were very repeatable. Now, there's a slight exception to that. After we started to get significant downslope erosion, where there was an accumulation of bentonite, started to cause a stick-slip issue. So we did notice, and knowing it was there, you could go back and look at the photographs, and you could see the photographic evidence, which we now know was telling us that something was happening, but at the time we didn't.
Do you see more managed thermal expansion contraction with supported or reinforced geomembranes?
Haven't really looked at it, so I'm not sure I can give you an informed answer to that question.
Okay.
I do think the issue can be solved by just controlling when you cover it.
Okay.
Yeah, can I just add, though?
Sure.
That is something I would give responsibility to design engineers for, because it needs to be in the specification right at the outset, so that the contractor bidding on it knows what the game rules are and knows that there's going to be a quality assurance inspector there checking, and they price appropriately. And if you want a good job, expect it's going to cost you a little more.
Sure.
And you'll save money by the problems you don't create.
Great point. One more question, Dr. Starr?
So Kerry, in your equation where you added the wrinkle flow, plus 2qn, you had transmissivity, but isn't it also Darcy's law, Q equals KIA? Now you have a bigger area over which the leachate liquid is acting, and so don't you have to include the cross-sectional area that the liquid's now contacting the GCL or CCL?
Oh, that's all.
You probably should repeat that question.
Oh, no, go ahead.
No, that's
Okay.
okay. You go ahead.
The question was, in the equation I gave, it was very clear that it was considering the area beneath the wrinkle. It wasn't so clear it was considering leakage outside the wrinkle. Just as if you use the Giroux equation, you don't know anything's happening outside the hole. It's all built into the equation. It is considered, and in fact there's another equation in my 1998 paper, Atlanta Geosynthetics Conference, where I not only gave that equation, but I showed you if you've got interaction, how you can take account of interaction between parallel wrinkles, and it tells you exactly what the wetter rate is. You can calculate it. It's just that if you want to know leakage, you don't need to know that equation that gives you what you really need.
Yeah.
Is there time for a final comment?
Quick,
10 seconds.
Sure.
About the question regarding the black or the white geomembranes, right? What should be used, and also commenting on Sam's, question. It's not only deciding the color of the geomembrane, because here you talk only about polyethylene, right? The designing process also should consider different types of geomembranes that would tackle very well this kind of wrinkle stuff, all else equal, right? Bringing no problems in the other variables of the project. That's my comment. Okay.
Yeah, so the comment was there should always be some consideration in the type of material. Dr. Rowe's presentation focused on HDP, and there are other materials that may not, that just may have differences in.
Oh, absolutely, and it's there's an old expression, horses for courses. Pick the right geomembrane for your particular situation.
Right. Great. Well, thank you again, Dr. Rowe. That's the end of both your presentations today, which were both great. Excellent job, and we really appreciate you coming to the University of Illinois today, and the topics that you present on were very, very relevant to everything going on in the industry. So once again, let's thank Dr. Rowe.